Hello, Linda.
Yes, hi.
I think we can start so that other people can join as the seminar progresses. We
Sure.
wouldn't have to wait for too long.
Sure. Sounds great.
So let me introduce, ladies and gentlemen, we are welcome to this seminar, our Fast for Future regular monthly seminar for the month of November 2025. The seminar today will be presented by Dr. Linda Straub. She's already here waiting for us. Dr. Linda Straub is a science education consultant and a co-director of the Pan-African School for Emerging Astronomers, PASIA. Linda has been one of us for so long, has been working for us in Africa on different platforms. And this evening, she wants to present to us a seminar, or rather a mini workshop that has to do with STEM education based on her experiences working in the African context. So Linda will be talking to us in the next 1 hour, and after which we can interact with her. So, but Linda, before you start, I think it would be good if you introduce to us your consultancy services as far as science education is concerned. So thank you and welcome to this seminar. So over to you, Dr. Linda.
Thank you. Thank you very much, Dr. Odo. It's a real pleasure to be with you all today. Let me see if I can start sharing my screen and show you my slides. All right. Great. Can you see my slides? Can you see my screen?
Yes, we can
Perfect.
say.
Thank you.
Yeah, we
Okay.
can.
Thank you. Thank you. Well, I want to thank Dr. Odo and Dr. Ofodum for inviting me to speak to you today in the FAST4Future seminar. It's a joy to be here with you today. And I am going to be talking about STEM education and teaching, as the introduction said. So the title of my talk is How Big, How Bright, How Far? Teaching Astronomical Inquiry at PASEA and UBC. And PASEA is, as Finbar said, the Pan-African School for Emerging Astronomers, and UBC is the University of British Columbia in Canada. And that's where I'm based, is Vancouver in Canada. So as was mentioned in the introduction, I'm a science education consultant, and I've had a sort of unusual career path. So I'll start by telling you a little bit about that, and then we'll get into the inquiry and PASEA. So I've been doing independent consulting for the last few years. I have a small business, which is just me, called Strava Educational Consulting. And my mission is helping people around the world to feel joy, empowerment, and community through astronomy and physics. And I started with studying theoretical astrophysics. So my PhD is from UC Berkeley in California in the US. And then I moved to Canada in 2012 to do my first postdoc at the Canadian Institute for Theoretical Astrophysics, where my research focus was a process called the tidal disruption of stars by massive black holes. So, as you probably maybe know, almost every galaxy has a massive black hole at the center. And occasionally, a star can wander so close to the black hole that it gets ripped apart by the tidal gravity of the black hole. And when that happens, the gas that used to make up the star ends up some accreting quickly onto the black hole, some getting pushed back out into space, and it creates this bright flare that can be observable for days or weeks or months. And so my research was on predicting what those events should look like at optical wavelengths so that we could find them and interpret them. But along the way, I got more and more interested in education. And about 10 years ago, I decided to transition from being a theoretical astrophysicist to doing astronomy and physics education and professional development, which means teaching other people about teaching skills. And to do that, I've had a few different roles. I started by doing a postdoc at the University of British Columbia. I was a science teaching and learning fellow for 3 years. Then I did another postdoc in physics education research at the American Association of Physics Teachers. And then now for the last few years, I've been doing educational consulting for various organizations, including the American Astronomical Society and the American Physical Society. And as a science education consultant, I get to do lots of different things related to science education, which is part of why I enjoy it so much. So I do professional development in teaching. As I said, that's helping other people learn teaching skills. I do a lot of program evaluation for science education projects. I'm the project lead for a workshops for African astronomy teaching called Blue Shift Africa, which I'll tell you about at the end. And I was the co-director for PASEA. I've done curriculum development, education research, and taught physics and astronomy. So lots of different things. And I'll tell you a little bit about some of them in this talk today. So that's a lot about me. I'd love to hear a little bit about you. If you're willing, I invite you to write in the chat your name, your institution and country, your academic level. Are you a student? Are you a lecturer? And what you're studying. I'm going to be quiet for just a minute and give you a chance to do that. Thanks. I'm not seeing anything in the chat. Would anybody like to share a little bit about who you are? There you go. Thanks, Sam. Nice to meet you. Oh, great. Nice to meet you, Ines Mohammed.
I think you can go into the seminar proper.
All right. Sounds good. Well, so the work I'm going to tell you about is taking place in a few different parts of the world, in Canada and in Africa. So I'm going to tell you about work that I did at the University of British Columbia, but first about work from the Pan-African School for Emerging Astronomers, PASEA. And as I noted, so I'm a co-founder and I was a co-director until earlier this year. So the Pan-African School for Emerging Astronomers is an innovative short course in astronomy for African university students. And it has been held so far 6 times in Abuja and Nsukka, Nigeria, in Accra in Ghana, in Livingston, Zambia, and most recently last year in Monastir, Tunisia. And if I'm not mistaken, it's going to be held in South Africa next year. The vision of PASEA is to contribute to building a critical mass of astronomers across Africa, to contribute to building community among African scientists, and to share ideas about teaching and learning between Africa and abroad. And now I wanted to ask another question. Maybe I won't pause as long, but I wonder if you've done any teaching so far. Some of you have noted something about that in the chat. I'd love to know about your teaching interest and experience. Is there something else we're going to? Yeah. And then actually I have a question that is perhaps even more important. So I hope you'll participate in this one. So when we teach, or perhaps you've noticed as a student, we often focus on teaching scientific concepts like what is a star or how does gravity work? But there are also a lot of practices that are important for doing scientific research that are beyond just understanding the concepts. For example, I've written here like reading and interpreting journal articles. And I am curious what you think are some practices that are important for scientific research. I'll wait for 30 to 45 seconds and see what ideas you have here, because that'll help set us up for learning about inquiry-based teaching, which is the focus of the talk. Practicals and hands-on lab work. That's great. Thanks, Sam. Oh, now I get to see some more of the introductions. Great. Awesome. Thank you. Well, if anybody else has ideas, please add them into the chat. And I'm going to now share with you a list, but it isn't a complete list. And so it's highlighting really the importance of scientific practices, which is to say that when we do scientific research, we're doing so much more than just understanding concepts in astronomy or physics or whatever. A very important scientific practice is asking questions. Some more are developing and using models, planning and carrying out investigations, communicating information, mathematical reasoning, reflecting on and reacting to experimental results. And then there are also some things to do with confidence and our identity, like feeling empowered to do science and feeling like a scientist. And so all of these are really important parts of becoming a great scientific researcher that are beyond only learning scientific concepts, which is obviously critical as well. But these often get less emphasis when we're teaching. And so what I'm telling you about today is a form of teaching called inquiry-based teaching, where students learn science in ways that mirror authentic scientific research, which is to say that scientific practices and scientific content are intertwined. So it isn't just learning the content on its own. It also isn't just learning the practices on its own. They're happening at the same time. And the format for inquiry that I'm going to be telling you about has 3 phases. The first is engaging the learner, so having learners ask their own questions. The focused investigation, where students do their own investigation on a topic that they're interested in, related to the question that they asked. And then the last step is making meaning together, so synthesizing and sharing results. I'm going to have you, maybe there's too much interaction in this and it's not the right vibe, but I'll try and give a minute and see if you feel like or are able to do this activity. So this is an example of engaging the learner to ask questions. And this is a piece of what we actually do in the inquiry activity in PASEA. So I am showing you here 2 images. On the left, it's the sun with some of the largest sunspots ever recorded in 2000. And on the right, it's the Pleiades star cluster. And so I'd like you to choose one of the images and then type in the chat What questions do you have about the object? What are you curious about? What sort of like stands out? What features stand out to you as you look at the image? What would you want to investigate if you could? And so I see some people are writing some stuff in the chat. So I'm going to wait a moment and let you write some questions. And thanks, Aman. Thanks, Julius. Thank you, Jude. And if you're not sure as yourself, you could put on your undergraduate student hat and think about what undergraduate students might ask if you are not one. Nice. Thanks, Julius. Thanks, Sam. Thanks, Jude. Absolutely. These are all really great questions. So we have like, why is the sun yellow? What are these things? Why does the cluster keep its shape? Yeah, what are stars? What are galaxies? What are sunspots? Where is the Pleiades star cluster located? Why is there color? Why is there a circular black spot unlike others on the sun? These are awesome. So thank you. Nice to meet you, Aman. So yeah, these are awesome. I think you're really getting into it and getting the idea about like how we can ask really interesting questions about just looking at astronomical images and how the images can prompt us to connect with our curiosity. And so this is totally something that students can have a great time doing and is really valuable for the scientific practice of asking questions. So what you just did is a very mini version of one step in the inquiry activity that we do in PASEA. So the first step in PASEA inquiry is a hands-on challenge. So measuring the distance to a model planet in a field. And if my Zoom works properly, I'm going to show you a video of that in a moment. We also do a hands-on experiment where we derive the inverse square law for light with a flashlight and shadow makers. Then the next step is for students to ask questions about astronomical images. So that's like what you just did. And we have a bunch of images around the room, not just the sun and the Pleiades, but lots of different astronomical images. And students ask things just along the lines of what you did, like, why does it look like that? What are those things? Why does it have its shape? Where is it? All that kind of stuff. And then students choose their own question to study in a group and break it down to focus on distance. So this is my first mentioning of how this activity is actually going to be all about distance. As I'll mention more in a moment, it turns out that very many questions that we can ask about astronomical objects come down to distance. So anytime we want to know how big something is, how far, obviously, or how bright it is, we need to know the distance to the object. And many questions that are along the lines of what is that? What is that black spot? What are stars, etc., turns into characterizing that object. We want to just understand what are all the physical properties. That's part of describing what something is. And if we want to know how big it is, then we need to know how far away it is. And so many questions that students ask can turn into a question related to distance. And so that's really the focus of this inquiry activity. So then students work in teams to plan a distance measurement to their chosen object. Then they discuss their results and process in different groups and reflect on their learning. And so the overall goals of this activity are for students to learn the distance measuring techniques of parallax and the inverse square law for light, and that students will value and gain confidence in scientific practices, especially breaking down big questions into smaller ones and doing investigations. The reason is that distance measurements underlie so much of what we know about the universe. The size, the brightness, the expansion, the energetics, all of that requires us to have measurements of the distances to different astronomical objects. that's one reason. And another reason why this is a great topic is that parallax and the inverse square for light are the same techniques that we can use right here in our everyday lives on Earth. And so I'm mentioning the idea of parallax a bunch of times, and I'm wondering if you've heard of that before. Maybe you all have, maybe you haven't. I just want to check in. So can you either write in Zoom or you can raise your hand if you do know what parallax means? Julius, thank you. Who else? We've got Jude says yes. Great. And as Mohammed says yes. Okay, cool. So a bunch of you do. Maybe everyone does. Maybe not everyone does. I'm just gonna do the fun little parallax experiment together really quickly. So you may have done this before. What I would like you to do, if you'll join me, is take your finger and hold your arm right out in front of you and line up your finger with something far away in the background. So for me, I can see some trees out the window. And so I'm going to line up, I'm going to close one eye. So I've got my right eye open and I'm aligning my finger with a tree. And then I'm going to change which eye is open. And I watch my finger kind of jump. Now it's no longer in line with the tree. It's in line with with another tree, basically. And now you can bring your finger closer to your face. Again, align your finger with the tree or whatever background object you have, and then change which eye. And my question to you, you can write in the chat, is as you move your finger closer to your face and you do the experiment I just described, does it appear to jump more or less? And you can type in the chat more, less, or the same. If this is new to you, please definitely try it. If it isn't new to you, I would like you to put on your undergraduate student hat and remember a time when you didn't know how this worked. And you can write it in the chat as well. Thanks, Inyama. Thanks, Jude. Wait just another moment. Sweet. I'll do this fun little experiment. All right, so I think we get the idea. A few of us wrote more. If you haven't done the experiment yet, I encourage you to do it. And so, yeah, that is right. And it may not seem like it at first when you learn about it, but that simple experiment actually helps us to measure the distance to faraway objects using trigonometry. So this is a really simple diagram of what that looks like for a planet being observed from two different locations. So if we observe the distance to, if we observe the alignment of a planet with a background object like a star, and then we move to another location, we'll see that the planet no longer looks in line with that background object. There's an angle. And by measuring that angle, theta, and the distance between our two observation points, this is called the baseline, L, we can infer the distance d without actually going there. And so that's what the inquiry activity warm-up is about, telling students to try and figure out a way to measure the distance to an object, and a hanging model planet in a field where you can walk anywhere you want along kind of a sidewalk that's the surface of the Earth, but you can't actually go there. So how can you do it? And so students work together in teams to figure out how to do it. And now I'll just remind you about, or teach you if you haven't learned about it before, about the physics of how parallax works to help us measure the distance to solar system objects. So for objects in the solar system, our baseline is the size of the Earth. So instead of just the distance between your eyes, we make that much bigger. And if we stand on two different locations on the Earth and look at Venus, for example, and use the sun as our background object, we can infer the distance to Venus, and then actually, through a few more steps, that can tell us the size of the Earth's orbit. And then what's really cool is that allows us to measure the distance to nearby stars. So in this diagram, now instead of using our locations on opposite sides of the Earth or our two different locations of our eyes, we use the location of the Earth at two different points in its orbit, two different ends of its orbit around the sun, because of course the Earth is moving. So we just measure it at two different times of year and relative to the background stars. So in this diagram, we're measuring the distance to this star. We line it up in September. It looks aligned with this star. In March, it looks aligned with this star. We measure that angle. We know the distance from the Earth to the sun. We measured it in the previous step. And so then we can measure and infer the distance to that star. So that's why parallax is really important for our understanding of distances in astronomy. It's a really critical tool and a really useful concept to understand. And at the same time, it's based on things that we just do right here in our everyday lives on Earth. So here's some of the kind of data that we give to students to allow them to make measurements like this. So this is an event that took place in 2004 called the Transit of Venus. And it's basically this, what happened here, where Venus was in line with the sun, between the Earth and the sun. So that doesn't happen very often. It happens twice every 112 years, if I remember the numbers right. So there was a pair of these events in 2004 and in 2012. If you observed the Venus in front of the sun, so these dots here are Venus, the yellow is the sun, these black bits are sunspots. The Venus does not look like it's in the exact same place if you observe from two really different places. So Anchorage, Alaska is like very, very far north. Sydney, Australia is very, very far south. And so these two, you can see there's sort of two offset dots here. One is what it looks like from Anchorage, and the other is what it looks like from Sydney. And by knowing the distance between those two locations on Earth, you can, and this angle, you can measure or infer the distance to Venus. The same idea happens when we want to measure the distance to the moon. So the moon occasionally occults, lines up with and blocks a bright star. It's doing it for faint stars all the time, but a bright star like the star Regulus. And that looks different from different places on Earth. So these are the names of a bunch of different cities. They're shown here. This is taken from a North American publication, so that's why they're all here. But obviously, this can be true for anywhere in the world. And so if you were in Atlanta, let's say, observing this event, you would see Regulus just graze behind the top of the moon. And if you were in Lima, Peru, you would see Regulus just graze the bottom of the moon. And so by knowing the distance between those places on Earth and the angular size of the moon, you can again infer the distance to the moon. So now what I'd like to do, but I'm afraid Zoom might not let me, but I'm going to try, is to show you a video of students engaging in the Hanging Planets Inquiry activity at our PASEA 2017, which back then it was called YCIA, in Accra, in Ghana. So if I start playing this, you can let me know if you hear the sound or not. There is no sound right away. Just a moment. Can you hear it or no?
Your mission is to measure the distance to the balloon, but you cannot walk over there. And our job is not to tell you the answers.
I'm just pausing it for a second. Can you hear it or not?
We can hear it, Linda.
You can? Okay. I got some warning when I started. Well, I hope everyone recognizes the famous person in the back here. Okay, I'll keep it going then.
Our job is to basically guide you, help you if you get really stuck.
Leave it, Angela.
Open that down.
I think in feet, like a basketball goes for, I think, 10 feet. It's 10 feet.
Yeah, around those 75, 70, around those areas.
So if we can imagine that's from that point to that point is 75.
Yeah, so we're able to get the angles.
Yeah.
We're able to get it.
Okay. We measured this angle. This is what we measured. That's what to be 65.
Yeah, 90 minus theta. Is this cos 90? I don't know whether I'm making a mistake or... This is a bearing question that you're trying to solve. So we being here, we've taken this
Distance.
This distance
From here to here, 15 meters.
So where is it on the ground? Yeah, 50. That's it.
Yeah, that's it.
So if it is here, let's put her, and let's just say maybe 15 meters, and we are looking at through the angle like this. Do you see that? When you look at the house, it's not in line with the planet. But when you stand at this point and you look at it, it's in line.
And we stand here to get, and then we move this way. So we have our 90. So you go and stand here and just look at it. And then now get this. And then we measure this.
Yes.
Can you say that again?
Yeah. So are we on track? Yeah.
All right. So thank you for watching that with us. That was the Hanging Planets warm-up activity in YCA 2017 in Ghana. And you can see that students were given this challenge problem, and they had to figure out in teams how to measure the distance to a planet. And as they do that, they're building their skills of working together and figuring things out, making models, drawing diagrams, and figuring out scientific concepts related to them. And so, let me see, slideshow again. Yeah, and so after students do that warm-up activity that we just watched, they then, as I mentioned, they then ask their own questions about astronomical objects, just like you did, about the sun and the Pleiades, and then they work in teams to figure out the distance. So this is students from PASEA 2019, Mary Queen, Jane, and Esther figured out the distance to the moon using a lunar occultation of Regulus. And you can see here the post-it that they made, their diagram, their math for figuring it out, and also their happy faces. We also have Samson, Dorcas, Josiah, and Jude, who I think is here, figured out the distance to a nearby star cluster using parallax from the Earth's orbit. And one student wrote about PASEA, and doing this activity, PASEA made me realize that I can think and find answers to questions on my own without external help. I can now say I can think like a scientist. So these kind of results and feedback are just, a joy to be part of, and really emphasize the importance of doing our own scientific investigations in teams as part of our learning to help us to think like a scientist and learn the skills that we need to get ready to do scientific research. So now what I'm going to do is take us to Canada, where, so we designed this, the PASEA team designed this activity for PASEA, for African students. And then I was, at the time, a postdoc at the University of British Columbia in Vancouver, Canada, over here. So we wanted to redesign the lab courses for an astronomy, the lab component of an astronomy course at the University of British Columbia. So I'll start by just showing this is the University of British Columbia, this area, and this is Vancouver. And I'm really grateful to live in such a beautiful place. I live sort of somewhere over here. It's lovely to be close to the ocean and the mountains. And we did our Hanging Planets inquiry activity outside on campus. So the course where we did this transformation is called Introduction to the Solar System. We have about 100 first-year undergraduate students. They are science majors, but not physics or astronomy majors. So many of them are studying biology or chemistry, for example. And they have 1 2-hour lab per week. And so what I kind of want to be showing here is how we were able to take what we designed as a 2 full-day lab activity for PASEA and turn it into a 5-week activity for use in a more like formal classroom setting. So we divided, or we broke down the inquiry activity into 5 weeks of activities. So Lab A is the parallax challenge problem. That's the one that we just watched the video of with PASEA students, but now this is with students in Canada. Then the second week is the inverse square law challenge problem, which I haven't gone into detail, or I haven't told you about particularly, but that's figuring out the inverse square law for light. That's the concept that says that something that has the same intrinsic brightness looks fainter when it's further away. And so that's another way that we measure distances. In Lab C, students ask questions about astronomical images. They choose a question to investigate, and they break the question into investigable parts. In Lab D, they investigate their question in groups. And in Lab E, they present their results to their classmates. So this is what that looked like for UBC students. Here they are trying to measure the distance to the same hanging planet without being allowed to cross the sidewalk here. This is Lab C. And you can see some of the questions that students asked, like so this is just two images related to the sun. So what causes the flare and how big is it? What are the effects on Earth? What is the solar prominence? And there's lots of different great questions, and we circle the ones that are to do with distance, and then students get to investigate that. So what were the effects on Earth? That's going to care about how far the Earth is from the sun, or how big is it? Again, that in order to know how big it is, we need to know how far away the sun is from us. And then this is a presentation from a student group that wanted to know what is the density of the moon, and to figure out the size of the moon, which is part of the density equation. They had to know they had to figure out the distance to the moon. So now I want to just tell you briefly about assessments of student learning. So it's really important when we teach to make sure that our students are learning the things that we hope that they're learning, or rather to find out what it is that they are learning, so that we can, refine our methods of teaching and see what's working and make any changes that we need to. So one of the ways that we do assessment of student learning in PASEA is a survey called the Colorado Learning Attitudes About Science Survey, or CLAS. And it's a survey where there are a bunch of questions that you have to rate your level of agreement with. So for example, when I'm solving a physics problem, I try to decide what would be a reasonable value for the answer. or I think about physics I experience in everyday life. And this is designed for physics, but the same ideas come for astronomy. And what we found is that PASEA students' attitudes become significantly more like experts over the course of doing the full PASEA, but I think the inquiry activity in particular. And compared to typical courses around the world, this is a rare achievement. So I think inquiry is showing how powerful it is at helping students develop scientific attitudes. For student learning at UBC, we asked students to reflect on their learning and write about it. And some of the themes that we saw are that students really appreciated having freedom to come up with their own approach in the lab. So unlike many labs where you're told, do this, do this, do this, do this in this order, it was really student driven. Like they had the question that they wanted to investigate, but it was up to them as a group to figure out how to do it. And students said that this was helpful for learning concepts and problem solving. It was more interesting, it encouraged creativity, and it felt more like real scientific research. Students also discovered that real life science is challenging, not surprising, but also powerfully, 2 ways to help succeed through the challenge are breaking big science questions down into smaller ones and working together in a team. So that's kind of building students' self-efficacy to do their own scientific investigations in the future. Self-efficacy meaning like confidence, the belief in yourself that you can do it. A few quotes from UBC students. This week's lab was different in a positive way compared to other labs I've done. We weren't just given a step-by-step recipe to follow, but had to come up with a plan by ourselves, which I found both rewarding and challenging. Another student said, we were very actively involved with the material, and we essentially had to solve the problem for ourselves with almost no help. It really helped me to improve my critical thinking and problem-solving skills. And then one PASEA alum's daily reflection, they wrote, I really love the way we were allowed to discover parallax ourselves. I wish learning in school was as interactive as that. So that's been an overview about inquiry, where we have these 3 phases of engaging the learner, the focused investigation, and making meaning together, and looking at assessments of student learning, which we found really positive feedback from students. Now I'm just going to take a few moments to talk about how we teach or facilitate inquiry, and in particular preparing the graduate student teaching assistants that we had at UBC, and also teaching the instructors that we have at PASEA when it's the first time for them facilitating inquiry, because it's different from teaching sort of typical labs where you go around and just kind of answer students' questions. The important steps are to do a lot of observing and listening and asking questions rather than answering them. So finding out what students are learning and, what learners are doing and thinking. Giving learners time, space, and encouragement to figure things out themselves, resist giving them the answer, and to help make sure that all group members are active participants. So if somebody's being really quiet, to encourage them to participate more. And so what we did was have the TAs first do the labs pretending to be students, then reflect on the experience of inquiry, then discuss any facilitation strategies that they observed, and that when they taught the lab for the first time, to be paired up with an experienced facilitator to get feedback like while they're practicing teaching. So this is kind of the professional development aspect of this. And one teaching assistant said, I learned to give room for students to explore, take a more observational approach near the beginning, only starting to guide and step in as things progress further. 2, students will struggle somewhat. It's important to let them try to work through it before giving too much direction. And 3, there's not a proper way to go about figuring things out. Of course, we have goals that we want them to reach, but they may come up with a novel way of doing so. And I feel like this TA really captured the essence of what we were trying to support our TAs in learning about how to facilitate inquiry. It's a lot about giving students freedom and only kind of like giving giving guidance and nudges as needed, but really supporting students to have the freedom to explore, because that's where a lot of the learning happens, and also the enjoyment of it. So we have published a journal article in the journal Course Source about this work. So it's called Distances in the Universe, an inquiry lab sequence taught in West Africa and North America. We describe all of the things that I've told you about today and in much more detail, and all of the curriculum documents are available for download. So if you teach an astronomy course or a physics course and you want to involve some of this, you can go and get all the materials you need from this article. We also published an article about Pasea itself in 2021 in the journal Nature Astronomy. And if you want to check that out, I invite you to. And then the last thing I want to tell you about is a newer project that I've started working on this year called Blue Shift Africa, Building Learning in Undergraduate Education in Astronomy. And it's sort of taking the beginning professional development ideas that we have in the training for Pasea instructors and making a whole workshop and project out of that. So I'm the project lead. I'm working with a liaison from the American Astronomical Society, Dr. Tom Rice, and recently started working with my co-facilitator, Tabita Alango, and we have a lot of other contributors to the project as well. And this is made possible by a venture grant from the American Institute of Physics. And so the project really focuses on undergraduate education, which sometimes gets overlooked a little bit, but it's a really crucial bridge between secondary and postgraduate. It's the time when students decide to become a scientist or a science teacher or pursue postgraduate studies, and it lays the foundation of scientific content and scientific practices. So how we teach undergraduate science is important. Many of us have been taught by a pure lecture, so just having somebody stand at the front of the room and just talk to you. But there's a wealth and growing body of research that shows that teaching in interactive ways is more effective and inclusive than pure lecture. So the purpose of this project, Blue Shift Africa, is to teach early career scientists some of these interactive techniques for teaching. So we started with a pilot study about undergraduate astronomy teaching around Africa. We have 2-day workshops on undergraduate astronomy teaching at the African Astronomical Society conferences this year and next year. We have online communities of teaching for workshop participants, and we're going to have a panel discussion next year. So here's the group in March of this year at the University of South Africa in Johannesburg. We had 23 participants from 9 countries, and the workshop topics included strategies for teaching, for interactive teaching in astronomy, research-based principles of effective teaching, teaching to promote equity and inclusion, and case studies of teaching scenarios from participants' experiences. So if you are an early career scientist or lecturer with at least a little bit of teaching experience, I welcome and invite you to join us for our upcoming workshop, which is going to be at the African Astronomical Society meeting in Kasane, Botswana, March 20th and 21st, I believe. It's here, 21st and 22nd. So if you're interested, the call for applications is going to go out to the FS membership list soon, and you can check out this website to learn more. So that has been my talk on how big, how bright, how far teaching astronomical inquiry at Pasea and UBC. It's been a joy to get to talk to you today, and I'm happy to answer any questions that you're interested in. Thank you so much.
Thank you, Linda, for that wonderful presentation. I really appreciate the time you took. Can you hear me?
I can hear you. Thank you, Afodum. It's great
Yeah.
to hear you. Thank you.
I'm on the road. Sorry.
Okay, no problem.
So yeah, I really appreciate the time you took and the effort you made in explaining all these things to us. And I know that most of us that took part in this presentation learned a lot from what you said. I know that ordinarily we have far more number than this in our previous seminars. But this is the first time we are having this seminar by this time of the day. We normally have our seminars around 10 a.m., 9 a.m. in the morning. But because of the wide gap in time zone, we have to find a way to accommodate your time zone so that it will be a bit more convenient. Whatsoever you presented to us is recorded. The seminar today is recorded, and most of our participants do go to the FAST4Future website to watch the video at their own convenient time. So I'm sure that so many of us will still go back to those sites to watch what you have.
Sure. Thank you, Afodum. That's great. And yes, I appreciate all of you, your flexibility in letting me speak now because the time zones are difficult, as you said. Inyama, do you want to say something?
Yes, I have a question. Can you hear me?
Yes, I can hear you.
All right, thank you. So I want to find out,
Presented to us.
like,
So, hear me.
Uh-oh.
Hello? Can someone hear me out there?
Afodum, we could hear you, and then we stopped hearing you.
Sorry, the network is bad.
That's okay.
So, what I was saying in actual sense, the majority of us will still go to FAST4Future website to watch what you have presented to us. And we do appreciate your effort. We also heard what you said about the upcoming workshop, that is the Blue Shift Africa. And I know that majority of our participants will join during the workshop.
Great. Thank you, Afodum. And as I was saying, I really appreciate your flexibility about the timing. Inyama had raised their hand, so do you want to go ahead, Inyama? Sorry, you were starting to say?
yeah, I want to ask a question. Like, in the inquiry-based teaching method, does like asking the students about the questions, like trying to get them to think about the problem more deeply, considered an inquiry-based teaching, or you just let them like figure it out by themselves?
Hello?
I think you're asking if in inquiry-based teaching, you just let students do it by themselves. And I'll answer what I think you're sort of asking about. In inquiry, there's giving students space to ask their own questions, but then there's also the support to help students figure out the answer. So we don't expect that students will necessarily know how to do it. And in fact, it's better if they don't know how to do it because we want them to practice that skill of figuring things out. But the support that they get are, one, is working in a group. So getting to express their ideas to others and hear other people's ideas really helps students move along in figuring out the answer. And then there's the facilitators. So people like me will be wandering around and listening into what students are talking about and thinking about. And while we won't just directly answer questions, we'll ask questions that we know will help students in the right direction. We'll ask students to explain their thinking so far in ways that will help them to see like, oh, we haven't thought about this yet. So it's offering sort of like gentle guidance and nudges towards figuring out the answer. It isn't just like ask your own questions and we'll leave you alone. Is that sort of what you were asking?
Yes. I want to find out about where you ask them questions to like, yeah, probe them towards thinking more clearly. Thank you very much.
Great, thank you. Sam?
Yes, thank you very much for your presentation. And I think this kind of learning is very good because they get to ask questions and they are guided to get their own answers and create their knowledge. But I want to ask, before they start these projects, do you brief them? Do you give them some theoretical basis for them to start this this experiential learning? Or you just put them on the field and they explore?
Yeah, it sort of depends. So when we were doing it for the UBC students, we gave them some like pre-homework assignment that was basically kind of like a trigonometry review, so that they would have those ideas kind of like fresher. But we don't, for example, want to give them a theoretical overview about how parallax works before they go and do the warm-up activity like I showed you in the video. Because if you do that, then students are going to spend the whole time trying to interpret the the math or the diagrams that you gave them rather than building their own skill and capacity to design their own diagram, to figure out their own, like create their own equation. So we want to like give students enough kind of nudges to start being on the right track, but it is not like, here, I'm going to give you all the theoretical background and then you go and do it. It's kind of like the students figure out the theory themselves with support and hints from the instructors.
Okay. And one other thing, I think this method will work well or works well when you have smaller groups. What if you are dealing with larger group of students? And that will be very challenging.
Yeah, it can definitely be quite challenging. Ideally, you want to have students able to be broken into groups of like 4. 5 is all right too. And then you basically need people to facilitate those groups. So I think one facilitator for every like 20 students is like sort of doable. And so one of the ways that we do that is, you know, you maybe have only one like professor or head instructor, but you can get some graduate students, or it could even be like undergraduate students who've taken the course before to learn how to facilitate and then come and be facilitators during the inquiry activity if you have it in a larger class. So it does require like quite a lot of person power, but you can bring in students to help you. That would be my answer.
Oh, okay. Thank you very much. I'll get in touch. I'll take your email and then
Yeah,
I'll
please
write
write
to
to
you.
me.
All right.
Great.
Thank you very much.
Thanks.
Hello, Linda.
Hey, yes.
We have some questions coming to you on the chat.
Oh, okay. I didn't see them. Where's the chat? Maybe I'll stop sharing the screen.
The first question said, how can I be part of PASIA program? Are there galaxies that do not have black holes? And what type of galaxies are there? What is the difference between star cluster and star cloud?
Okay.
The second question read, can superclusters orbit black holes? So can you help us do justice to some of those questions?
Yes, let me have a look. Okay, scrolling back through. Okay, Jude is asking to make the video recording available. I will send it to Finbar and Afodum, and you guys can send it out. Sure, it's publicly available on the web, so no problem.
Okay.
Aman asks, how can I be part of the PASEA program? I suggest that you speak to Afodum about that. I was co-director until earlier this year, but now I sort of changed to focus on Blue Shift Africa, so Afodum can help you with that. Are there galaxies that do not have black holes, and what types of galaxies are these? Really, only the very smallest galaxies probably don't have black hole, or maybe don't have black holes, but we actually don't even really know because they have smaller black holes, and that makes them harder to detect because they have a smaller gravitational impact on the galaxy. So that's an active area of research. That's a great question. What is the difference between a star cluster and a star cloud? I think nothing. I think we might just call it a star cloud when it's like a gas cloud that's in the middle of forming into stars, and then that eventually becomes a star cluster. Can superclusters orbit black holes? Generally, or not generally, no. Like it could, but that's not how things have formed. Really, black holes sit in the centers of galaxies because they're the remnants of stars that, well, not all black holes. There's questions about how the first black holes formed in the centers of galaxies, but black holes are basically all part of galaxies. So there aren't like free-floating black holes that a supercluster would be orbiting around. And then why is there only blue and red shift? Why is there no yellow, purple, and orange shift? That's because blue shift just means towards the bluer end of the spectrum, so towards shorter wavelengths, and red shift means towards longer wavelengths. But green, yellow, purple, and orange, you could go towards any of those, but it's just about the direction of the shift. And Aman, you asked for my contact info. Hopefully you saw it on the screen. If you don't, let me know. And Nas asked, can the concept of parallax be used with telescopes to measure or observe things other than planets and stars in the deep universe, like observing something in the far universe? That's a really, really, really great question. And the answer is no, because the further the object gets from you, the smaller the angle is, the smaller that jump becomes. So if you imagine putting your finger like on the moon and you close your two different eyes, you won't be able to detect the jump. So there still is one. It's just so tiny that the kind of instruments that we have can't detect it. And so we can only use parallax, let's say halfway across our galaxy. But beyond that, we have to use other techniques like the inverse square law for light, which I don't have time to talk in detail about here, but I encourage you to look it up because it's the thing that we use to measure the things to the furthest parts of the universe. And then the last question I see here, what kind of memo do you use to assess lab experiments like this? Since students come up with their own, methods which could produce wrong or faulty results. There are a couple of things that we do. So I'm just putting my email in the chat again. There are a couple of things that we do. So one is we have active facilitators that are listening to and paying attention to what students are doing, like throughout the time that they're investigating. So what should happen is that students have this space to try out different things, but every so often a facilitator is coming by and saying like, tell me about what you're thinking so far. How did you come up with that? What's your plan? And can hopefully, or can kind of nudge students in the right direction, or help, or most ideally help the students to see what's wrong with their method before they've spent way too long on it. So that's one way. That's the best way, is to kind of like see it in real time. And then we also have students kind of present their results. So they might do a presentation to the class, they might write a lab report. And so these are some ways that the instructor can see what did the students actually get out of it, and then give students the feedback if their results were not right. But the real focus is the process of figuring things out. So even if students don't get exactly the right answer, they'll have learned a lot through the process, and that's the thing that's the key. Feel free to ask more things, but thank you for all the great questions, especially those in the chat. And thank you very much for the opportunity to speak to you today.
Thank you very much, Linda. On a final note, I've heard what you said. I'll get, because we have email address of almost all the participants, and we will get across to them as regards the upcoming PASIA, which, like you said, we'll get across to them to make sure that they have the opportunity to participate in it. Somebody was also saying that you should, if possible, drop your email address for them on the screen so that they can get across to you for further communication. I saw somebody dropping a chat now. Okay, thank you for that. You have done that. So, on a final note, I want to thank everybody for this wonderful opportunity. We hope to invite you one of these days, Linda, so that you can talk to us.
It would be a pleasure. Thank you.
Once again. So I really appreciate your coming and all you did for FAST4Future project. Thank you very much.
Thank you. Thank you. It's been a pleasure to be here with you all today. Thanks again for inviting me.
Bye.
Bye.
Bye-bye.